Hello friends, welcome back to subject fluid mechanics. We are studying basics of fluid mechanics. So in today's lecture, we are going to discuss about the fluid pressure. In last lecture, we have discussed about the remaining properties, that is capillary reaction, and bulk products of elasticity, compressibility of surface tension, stress problem. Today's lecture, we are going to discuss about the fluid pressure. So the learning objective of today's lecture is to know related terms of fluid pressure, to know about hydrostatic law. After the end of this lecture, it is expected that you will be able to know about fluid pressure as well as you will be able to explain about hydrostatics law and Pascal's. So, what is pressure? At early initial only during the discussion of syllabus itself, we have discussed about what is pressure. So pressure is defined as a normal force exerted by a fluid on unit. So here we are discussing related with the fluid, so that's why we have used terminology as a fluid. So what is pressure? Pressure is nothing but a force externally exerted on the body. That is called the pressure. So we speak of pressure only when we deal with a gas or liquid. Counterpart of pressure in solid is normal stress. So normal stress we are calling it as normal stress. In solid we are calling it as normal stress. Since pressure is defined as force per unit area, it has the unit of per meter square, which is called Pascal. We know that we have discussed earlier itself. 1 Pascal is the defined unit per meter square. The pressure unit Pascal is too small for pressure encountered. The fact is, therefore, it multiplies kilopascal or 10 or 3 Pascal and megapascal is called 10 or 6 Pascals are commonly used terminologies. Many times in the problems which we are going to deal or discuss, pressure is given in megapascals. When a certain mass of fluid is held in a static equilibrium by confining it within the solid boundaries, it exerts the force along the direction perpendicular to the boundary contact. This force is called as compression. It is defined as the normal force exerted by a fluid per unit area, and it is also expressed in terms of bar, and we know that 1 bar is equal to 10 or 5 Newton per meter square. Importance of pressure measurement. The pressure of steam in a boiler is measured for ensuring safe operating conditions of the boiler. Pressure measurement is done at various process industries such as manufacturing and chemical industries. Pressure measurement also helps in determining the liquid level in a tank and containers. And many flow meters such as a ventimeter, odipeximeter, flow nozzle, etc. Pressure measurement serves as an indication of flow rate. Measurement of pressure change becomes an indication of temperature also. This is as a pressure thermometer, fluid expansion, etc. Apart from this, pressure measurement is also required in day-to-day situation, which such as maintaining optimal pressure tubes and vehicle tanks. So these are some common practical applications we have discussed here. If you have visited a sugar plant industry, you will observe the pressure gauge there. Pressure gauge. If you have visited even in a farm also, if you have a water irrigation system, direct water irrigation system, then for there also it requires to measure the pressure of water, which is flowing through pipes for the pressure compensation. There are certain terminologies used for pressure: absolute pressure, gauge pressure, vacuum pressure. Before that, we will discuss about what is atmospheric pressure. Pressure at our surrounding is called as atmospheric pressure. That is we are surrounded with the air. We are surrounded with certain pressure of air. It is called as an atmospheric pressure. Since it is available in the universe commonly, that's why its effect is negligible. It's negligible. That's why it is called as an atmospheric pressure. Absolute zero pressure is nothing but the pressure measured with reference to the absolute zero pressure. Absolute pressure is nothing but by considering the absolute zero pressure, whatever the amount of pressure showing is called as absolute pressure. So, though we can say that atmospheric pressure now is equal to zero because externally we are wondering here and here that its pressure effect is not observing. So that's why atmospheric pressure effect is zero. But there is certain amount of absolute pressure. Absolute pressure is always positive. Then the gauge pressure is nothing but pressure measured with respect to atmospheric pressure, and it is always above the atmospheric pressure. So gauge pressure is called always in the positive directions. So that is why pressure measured with respect to atmosphere is called as a gauge pressure. So if surrounding pressure is above atmospheric pressure, then and then only gauge pressure shows. Then and then only gauge pressure shows. So another term is vacuum pressure. Vacuum pressure is nothing but pressure measured below the atmospheric pressure. Pressure measured below the atmospheric pressure is called as vacuum pressure. That is it zero pressure? No. It is greater than absolute pressure, but it is less than atmospheric pressure, and that's why it creating the effect of vacuum. And that's why it is called as vacuum pressure. That is, it is very low. Then here the formulas are given. Gauge pressure can be given as P absolute minus P atmospheric. Vacuum pressure can be given as P atmospheric minus P absolute. Pressure variation, depth of fluid. Now consider this is the container which is filled with water, and it has three openings. One is the top, one is the bottom, and another one is provided at the mid. So when we start all three corks at simultaneous position, we'll observing three different jets. We are observing three different jets, that is one strong jet, weak jet, and medium jet. Why it is happen so? This is happening due to the increase in pressure at the bottom phase, minimum pressure at the top. So by this it is observing that pressure is maximum increases with respect to the depth of fluid. But again it is essential that surrounding is covered with respect to the same amount of your atmosphere. For example, in a container, if we are filling some fluid, then at the top position we will observing minimum pressure exerted by the fluid, whereas at the bottom position we are observing maximum pressure at the fluid. And that's why you can observe many things where we are using for the storage of fluid. Generally, we are not providing any sharp corners at the bottom edges. Even we are providing the sharp corners at the top edges, maybe because at there the locality of pressure is less as compared to the bottom pressure. Even for storage of water purpose in your house, if you have any pot, that pot also you will observe that they have provided some concave shape and it is not of the sharp corner, but at the top end you may observe there is the sharp corners, because at the top corner there is no any concentration of pressure, but at the bottom edges there is the concentration of pressure, and that's why it is shown at the end. Now pressure variation in at rest, which is called as the hydrostatic law. The rate of increase of pressure in a vertically downward direction is equals to the weight density of fluid at that point. See, once again, the rate of increase of pressure in a vertical downward direction is equals to the weight density of fluid at that particular point. So we can say that gamma P by gamma Z is equals to rho into G. It's called as the weight density of fluid. Now consider the small cylindrical fluid element as shown in figure. Let delta A be the cross-sectional area of element, delta Z be the height of fluid element, P be the pressure on face AB, Z be the distance of fluid element from the pressure. Now here we have considered one container. In that we have considered any element at a location at a distance Z from the top, having the boundaries ABCD, on which delta AB is cross-sectional area and delta Z is the height of fluid. So there are two forces acting on the fluid elements. One is the pressure force on the part AB, which is called as the rho into delta A, and pressure force on the face CD, which is called as the P plus delta P by delta Z into gamma P by gamma Z into delta Z into delta A. The weight of fluid is given as density into G into volume. So rho G delta A into delta Z with its volume. So the pressure force on AB is nothing but pressure P applied over the area delta A. Pressure force on CD is nothing but P plus delta P by dz into gamma Z, gamma P by gamma Z into delta Z into delta A, and weight of the fluid is nothing but rho G into delta A by delta Z. So the pressure force on surface AB and AD are equals to the opposite pressure forces on the surface BC and AD are equal and opposite, and that's why these are neglected because they are at same level of height. So for equilibrium of fluid element, we can write this as P into delta A minus P into delta P plus gamma P plus by gamma Z delta Z into delta A plus rho G into delta A delta Z is equals to 0. Now removing out the common terms, P into delta A, P into delta A will cancel, minus gamma P by gamma Z delta Z delta A, so rho G delta A delta Z is equals to 0. So it can be written as minus gamma P by gamma Z delta Z delta A plus rho G delta A delta Z is equals to 0. So we can write as gamma P by gamma Z is equals to rho G, which is the hydrostatic law of motion, which is proven. So pressure variation at the rest according to hydrostatic law, gamma P by gamma Z is equals to rho by G, rho into G. So by integrating above equation, integration of gamma P is equals to integration of rho G dz. So P can be given as rho G Z. So Z can be given as P by rho G. Meaning that Z is nothing but pressure head. Pascal's law we have studied in the class of 7th or 8th only in Marathi. It's called as बंदिस्त द्रवावरती दिलेला दाब सर्व बाजूंनी सारखाच असतो. Same law we are repeating it here. Pressure or intensity of pressure at the point in static mass of fluid is equal to R dash. That is, if the fluid is consists in a closed container, the applied pressure in all directions remains same. That is called as Pascal's law. So Px is equal to Py or Pz. Pascal law is established by French mathematician Pascal. States that pressure exerted anywhere in confined incompressible fluid is transited equally in all directions. So that is why, suppose if we have put out a fluid inside our container and we have applied some pressure, and if the fluid is incompressible, then the pressure shown by the pressure gauge in all directions at any position remains constant and remains same. This is the example of Pascal's law. Pressure applied at one point of liquid transit equally in all directions. To prove of Pascal's law, consider an arbitrary fluid element of weight shape. Let angle delta ABC is equals to theta into mass at rest with three lanes perpendicular to the plane of paper. Its unity that gamma z is equals to 1. The forces acting on the limits are pressure force normal to the surface, weight of the fluid limit on the vertical direction. So both are shown at here. So here pressure force on the surface AB is equals to px dy into 1, that is z equals to 1. So area of AB is nothing but dy into dz. Pressure force on surface bz into the area of dz, and pressure force on AC is equals to dy area of force BC, that is dy into dx dz. So these are the three forces acting on. Involving three forces and equating between equals to 0. We can write this as dx dy into dz minus bz into dx into dz sine of 90 minus theta is equals to 0. So dx dy into 1 minus dz ds into 1 cos theta is equals to 0. So, but cos theta is equals to dy by ds, so ds cos theta is equals to dy. So, in this terminology, we can write dx dy minus dz into dy into 0. And finally, dx is equals to dz. That is, it shows that Pascal's law is valid. Similarly, we can prove for dy also. For equation 1 and 2 becomes dx is equals to dy is equals to dz, and it states that pressure intensity or intensity of pressure at a point in static fluid is equal in all directions. Similar function is obtained in a balloon also. When we are applying the air inside the balloon, the cross-sectional area or volume of balloon increases in all directions equally, and that's why it is going in volume increases in all directions. Applications of Pascal's law in automobile hydraulic brake system, hydraulic jack, hydraulic pressure. We are applying law of Pascal's. Hydraulic machines also we are applying Pascal's law. And now the measurement of pressure. Pressure measurement devices are two types. Actually, both are of analytical, that is manometer and mechanical gauges. In the manometer, there are simple manometer and differential manometer. In simple manometer, we call it piezometer, U2 manometer, simple column manometer. And in the differential manometer, U2 manometer and intermediate U2 manometer. So these are the manometer types which where pressure measurement is carried out with the help of mercury. This comparison of pressure is mercury. So we are considering that mercury is a very high dense fluid, and then that we are measuring the pressure. Similarly, pressure measurement can be also carried out by using some mechanical devices like a diaphragm pressure gauge, Bernoulli tube pressure gauge, deadweight pressure gauge, and bellows type pressure gauge. Where diaphragm pressure gauge, Bernoulli type pressure gauge, and bellows type pressure gauge is giving continuous continuous pressure, whereas deadweight pressure gauge is used to measure fixed level of pressure, whether it is achieved or not. For that purpose, we are using deadweight pressure. So this is about some we have discussed about the pressure. Next lecture, we will see next lecture. Thank you.